Hi everyone, it's Mrs. Suderman. We are going to look at complex numbers and roots. You can check this out also in Chapter 5, Section 5 for some additional examples. You can see in the graph of f of x equals x squared plus 1 below that f has no real zeros. If you solve the corresponding equation, so if you took x squared plus 1, set it equal to 0, and try to solve x, you'll get x equals plus or minus the square root of -1, which we know has no real solutions. However, you can find solutions if you determine the square root of negative numbers, which is why we have invented, instead of real numbers, imaginary numbers. So the imaginary unit I is defined as the square root of -1. You can use the imaginary unit to write the square root of any negative number. So here's this table. You can find this in your textbook. An imaginary number is the square root of a negative number. Imaginary numbers can be written in the form bi, where b is a real number and I is the imaginary unit. Kind of like how you see a coefficient in front of an x, like 2x, so we have bi. The square of an imaginary number is the original negative number. So if we have the square root of -1 equals I, as seen in the middle of this table, then the square root of -2, we know that we can split the square root of -2 into -1 times 2. So we could split the radical as well into the square root of -1 times the square root of 2. And the square root of -1 is I, so we have I square roots of 2. And then there are also a couple of examples right there, along with the algebra, if b is a positive real number, how you can find that in terms of I if you have the square root of a negative b. Let's look at some examples. So let's express the number in terms of I. So we have the square root of the negative square root of -96. The key to these is you're really going to simplify the radicals the same way you would on any other day, except in the end you're going to have an I in the front of the radical. So first let's factor out the -1 from the 96. So now we have the negative square root of 96 times -1. 96, the largest perfect square that we can get out of it is the square is 16. So 16 times 6 is 96. So therefore we could split the square root of 96 into the square root of 16 times the square root of 6, and then the square root of -1 goes at the end. Well, the square root of 16 is 4. We can't simplify the square root of 6 anymore, so we leave that there. And then we have that square root of -1, which equals I. So we would have -4 times the square root of 6 times I. But we always want to write our coefficient in the front, then I, then the square root, the radical of whatever is left over. So let's try solving this equation. We have 5x squared plus 90 equals 0. So proceed as you would any other day trying to solve for x. So if we subtract 90 on both sides, or add -90 to both sides, then we can divide both sides by 5, and now we're going to use the square root property and take the square root of both sides. So we get the plus or minus square root of -18. So if we were to simplify the square root of 18, we would get 3 square roots of 2, and we would take the negative out as I. If we were to check our answers and we plugged back in positive or negative 3i square roots of 2, it would turn out that it works, as seen below in this example. Okay, so we have a complex number is a number that can be written in the form a plus bi, where a and b are real numbers, and I, of course, is the square root of -1. The set of real numbers is a subset of the set of complex numbers C. Every complex number has a real part A and an imaginary part B. So complex numbers have the real and imaginary. Real numbers are complex numbers where b equals 0, and imaginary numbers are complex numbers where a equals 0 and b does not equal 0. That will make more sense in just a second. But sometimes, these are sometimes called pure imaginary numbers. Two complex numbers are equal if and only if their real parts are equal and the imaginary parts are equal. So they must look identical in order for two complex numbers to be equal. So let's Find the values of x and y in this example that make the equation 4x plus 10i equals 2 minus 4y times I true. So we have 4x plus 10i equals 2 minus 4y times I. And you can see that the real parts are in red, the 4x and the 2, and the imaginary parts are in blue, the 10i and the 4y. So let's take the real parts and set them equal to each other. So you have 4x equals 2, therefore x equals 1/2. And then the I part stays the same, so we set 10 and 4y, negative 4y equal to each other. Take the sign with it. Solve for y, and we get negative 5/2. So in order for 4x plus 10i to be equal to 2 minus 4y times I, then the real parts must be equal as we solved on the left, and the imaginary parts must be equal as we solved on the right. So let's look at another example. We have negative 8 plus 6yi equals 5x. Sorry about the bell. 6yi equals 5x minus I times the square root of 6. Then again, figure out what your real parts are and then the imaginary parts, and set the real parts equal to each other to solve for x. So you get negative 8 equals 5x, so x equals negative 8/5. And take the imaginary parts, the 6y and the square root of 6, basically anything, negative square root of 6, anything that doesn't have the I, so we'll leave the I there and take the other part. So 6y minus negative square root of 6, and solve for y. And those are the values that we should have ended up with. Okay, so negative 8/5 and negative square root of 6/6. Okay, now let's find the zeros of this function. F of x equals x squared plus 10x plus 26. So first thing we need to do is set this equal to 0 because we're finding the zeros. And if we do completing the square, so we move the constant term over and add a box to each side. Remember that the box is b/2 squared. So here b is 10, divided by 2 is 5, squared is 25, so each of the boxes is 25. Now the left-hand side is a perfect square trinomial that factors into x plus 5 times x plus 5, or x plus 5 squared, and the right-hand side is negative 1. Now we can take the square root of both sides. So we get x plus 5 equals a positive or negative, don't forget that sign, and the square root of negative 1, which is I. So then when we subtract 5 from both sides, we'll get x equals negative 5 plus or minus I. The solutions negative 5 plus I square roots of 10 and negative 5 minus I square roots of 10 are related. These solutions are a complex conjugate pair. So they're complex numbers. Their real parts are equal and the imaginary parts are opposite. So the complex conjugate of any number a plus bi is the complex number a minus bi. In other words, the a and the bi look the same, but the sign in the middle is opposite, therefore they are complex conjugate pairs. If a quadratic equation with real coefficients has non-real roots, those roots are complex conjugates. By the way, if you're only given one complex root, you can always find the other by finding its conjugate. So you can't have one complex root without its pair. So if we're going to find the complex conjugate of these examples, 9 minus I, it will become 9 plus I. We just switch the sign in front of the I, the imaginary part. For B, we have I plus the square root of 3. Well, we want to rewrite that so that we get A plus BI. The imaginary term goes second. So we have the square root of 3 plus I. So then now we just need to switch the sign in the middle, and that's our complex conjugate. For C, first again, write it as A plus BI. Here, A is not included, so it's 0. And we have plus negative 8 times I. So if we want to switch the sign in the middle, we have 0 minus negative 8 plus I. And we simplify, and we just get positive 8I. So on your own paper, these are going to be 2 of the problems from your homework that you will be assigned in class, or classwork. I want you to complete number 29, g of x equals 4x squared minus 3x plus 1. And number 31, g of x equals 3x squared minus 6x plus 10 by finding the zeros.